Hello everyone, my name is Young Yoon. I'm presenting the paper SG Toolkit, an interactive gesture authoring toolkit for embodied conversational agents. This is a joint work with Kunal Park, Minsu Jang, Jae-hong Kim, and Ki-hyuk Lee at Atri and KAIST. Embodied agents like social robots, game characters, and virtual assistants are getting popular and being a very promising interaction medium. The key difference from the other medium is that they have a human-like appearance. So we naturally expect that they communicate as we do, using nonverbal behavior. Nonverbal behavior might include facial expression, arm gesture, body posture, and so on. Nonverbal behavior make the agents look alive and human-like, as you can see this amazing robot from Engineered Arts. In the present paper, we focus on generating upper body arm gestures for given speech. Generating speech gesture for artificial agents is not an easy problem. Typical methods are keyframe animation and motion capture. These manual authoring methods give high quality gesture motion, but there is a downside that they require high production cost. Another solution is automatic generation. It has minimal production cost, but low quality at the same time. We aim to provide another option which is more efficient than manual authoring and gives a high quality than the automatic method. We had interviews with three experts working in different domains of game, education, and robotics. They agreed that the automatic gesture generation is necessary, but its quality is not satisfactory yet. To improve the automatic method, they said the toolkit should allow a user to alter the gesture motion by controlling some frames, and modifying abstract aspects such as style is also necessary to give an easier way to control gestures. And the toolkit should be platform independent so that users in different fields can use the toolkit. Let me show you a demonstration video first. You can input a speech text and click the generate button. Then you will have automatically generated gesture motion.
Welcome to the mall. Our mall is the largest shopping mall with over 250 shops, 8-screen Cineplex, and plenty of gourmet cafes and restaurants.
Then you might want a metaphoric motion at the position of the word largest. Select a specific time and craft the desired pose by moving or rotating joint of the 3D characters.
Welcome to the mall. Our mall is the largest shopping mall with over 250 shops, 8-screen Cineplex, and plenty of gourmet cafes and restaurants.
You see the generated motion is smooth overall as following the desired contour. We also have a collection of unit gestures. You can select one and add to the motion control track. And of course, you can move it along the timeline. If you want more dynamic motion for some region, then you would modify some style parameters.
Welcome to the mall. Our mall is the largest shopping mall with over 250 shops, 8-screen Cineplex, and plenty of gourmet cafes and restaurants.
Now I'm explaining how we implemented this. Our model is based on the automatic generation model, which generates gesture motion from a given speech. It is a neural generative model trained on a large corpus of speech gesture data. More specifically, it encodes speech audio and speech text and generates a sequence of human poses in 15 frames per second. On the base model, we added a pose control element that is represented as a desired human pose at specific time frames. The control vector is concatenated to the speech feature vectors. Style controls were also concatenated similar to the pose control. A style vector represents scalar values of desired degree of motion speed, space, and handedness. Here, handedness is defined as relative motion between right and left hands. We trained the model on the TED dataset with the loss function here. The Huber laws minimize the difference between referential human motion and the generated motion, and the Gann laws guide the model to generate realistic motion. The style term is to make the model care about the style vectors. Without this style term, the model tends to ignore style control vectors, which are somewhat weak signals. We exposed the model to diverse pose and style controls by randomizing control position and length. During the development, we used some objective metrics of project gesture distance to check the overall generation quality and the pose and style compliance scores to see whether the model follows the input controls or not. We conducted a user study to compare the SG toolkit to automatic gesture generation and keyframe animation. The user study consists of 2 sessions. First one is a gesture design session, where the participant creates gestures using the SG toolkit and using the manual keyframe animation. And the quality assessment session is followed. In this session, crowd workers evaluated the perceived quality of the gesture videos from the previous design session and automatic gesture generation method. In the gesture design session, we had 2 scenarios of rushed and relaxed, where the maximal authoring time is limited to 5 minutes and 20 minutes. This is the survey results after the use of SG toolkit and manual keyframe animation method. We asked the participants whether they were able to create a gesture as intended and whether the result gestures were appropriate to the speech. In the rushed scenario, SGT showed higher intention and appropriateness rating than manual. In the relaxed scenario, where the participant had enough time to create gestures, there was no significant difference between 2 conditions. In the post-experimental interview, the participants said that it was easy to create gestures with the SG toolkit because they could have an initial sketch by using the automatic generation, and they only had to add new gestures to some parts. But one participant had a concern that our imagination can be limited by an initial rough sketch. In the quality assessment session, we compared the 4 videos for the same speech. There is the referential human motion that is a kind of timeline, and we had gesture generated automatically. And the gestures from the previous gesture design session using the SG toolkit and manual keyframe animation. For each video, the participant rated appropriateness to speech and human likeness of motion in a 0 to 100 scale using a web-based video evaluation tool called HemBip, shown on the right. We have collected over 4,000 ratings from 120 participants. These are box plots for appropriateness and human likeness ratings. For the human likeness rating on the right, there is no significant difference between the conditions. But we could find interesting differences for the appropriateness ratings on the left side. In the rushed scenario, where the authoring time is limited, the SG toolkit showed higher ratings than the manual method. This indicates that users can create gestures more efficiently using the SG toolkit. The SG toolkit did not outperform the automatic method, but it still has benefits for containing a designer's intention, which is an important requirement, but not possible only with the automatic generation model. And in the relaxed scenario, SG toolkit showed higher ratings than the automatic method. In summary, we introduced a new gesture authoring toolkit. It gives a higher quality output than the automatic method and is more efficient than manual authoring. We accomplished this by proposing a neural generative model which accommodates fine-level pose controls and coarse-level style controls. The implemented SG toolkit is platform agnostic, and all the code for model, web front-end, blend animation is available. Feel free to utilize in your domain. This is the end of the presentation. Thank you for listening.